Chapter 18 discussion. We have two more functional groups to get to, thiols and sulfides. We'll cover those today. The remainder of this week will be spent just kind of rewinding and doing review of these past two chapters. Remember, we only covered these two chapters, but they were a little bit longer than our previous chapters, which is perfect timing because then next week on Monday and Tuesday you will have your exam. All right, so we'll close out all new material today and then we'll begin some review next class. Remember, we went over these functional groups that we were learning in Unit 2 at the beginning here. So just to summarize these Unit 2 functional groups. All right, we had alcohols, ethers, those special ethers, those epoxides, and then thiols and sulfides. We talked a little bit about properties of these functional groups at the beginning, specifically as it related to polarity and boiling point. Everybody's going to take a second and give me an example of each one of these functional groups here. What do I mean when I say an alcohol, an ether, an epoxide, a thiol, or a sulfide? All right, so alcohols and ethers are our oxygen-containing functional groups, differing by where the oxygen is. All right, if it's on the end with a hydrogen bonded to it, or a hydroxyl group, that would be an alcohol. If it's in the middle of a molecule bonded between two carbon atoms, that is an ether. And an epoxide is that special ether where we take that carbon-oxygen-carbon bond and we force it in to this ring structure here, that three-membered ring. Thiols and sulfides contain what element? Sulfur. And so if we look on the periodic table, sulfur and oxygen live in the same family, so they have the same bonding patterns. So a thiol is analogous to an alcohol, where instead of having an OH group, we have an SH group. And if thiols are analogous to alcohols, then sulfides are analogous to ethers, where we have that sulfur sitting in between two carbon atoms. Cool. So these are our functional groups that we've been discussing in this unit here. And again, we're going to spend some time talking about these last two, the thiols and the sulfides. Not as common at all as alcohols or ethers or even epoxides, but nonetheless they do play a role. One of your 20 amino acids contains that thiol functional group. All right, so we're first going to cover nomenclature of thiols. All right, and as we said, they're analogous to alcohols. So let's put down both an alcohol example and a thiol example. We'll stack these two next to each other so we can kind of compare and contrast. And I want everybody to take a second and name this alcohol for me. All right, what is that molecule we're looking at? All right, step one is to find and name our parent chain. And for alcohols, we use this suffix OL at the end. So for this molecule here, my parent chain are these 3 carbons. I have my OH group, my hydroxyl group on carbon 2. So this would be 2-propanol. All right, and let's just remind ourselves here, picking this apart a little bit. The prop means what? The number of carbons, right? The fact that I have 3 carbons. All right, the all is for that hydroxy functional group. And what was the AN for? It's not just propol, it's propanol. Why do we keep the AN in there? So yeah, be a little bit careful. Yes and no. So yes, because we have all carbon-carbon single bonds. Just be careful. We wouldn't call it an alkane though, because an alkane would imply there's no OH group on there, right? The alkane is an absence of a functional group. But yes, like alkanes, we have all carbon-carbon single bonds, so we keep that AN in there as well, right? So this is because we have all carbon-carbon single bonds. Remember we talked about mixing functional groups. If we threw a double bond in there, it wouldn't be a propanol, it would be a propenol. We would put the EN in there instead. All right, cool. So then we need a different suffix here since we have a new functional group. Our thiols, they got super creative with, and they name, or rather the suffix they use is thiol. All right, so we have our same 3-carbon parent chain here. We have that functional group again located on carbon 2. So 2-prop. I'm going to keep that AN for those single bonds, and then that suffix thiol. But what's the problem here? We've talked about this a little bit before. Yeah, the consonants here, running these 2 consonants together. We always avoid this in organic chemistry. Interestingly enough, our thiol suffix here doesn't start with a vowel, it starts with a consonant. So we're going to have this problem of running 2 consonants together. So what we're going to do is we're going to keep a vowel, specifically it's not going to be propenethiol, but propanethiol. All right, we're going to keep this E. All right, so that we don't run 2 consonants together. So propanol, but propanethiol. All right, so then let's just do an example here. I want everybody to take a second and name the following molecule for me. All right, so remember we want our longest continuous set of carbons, but that set of carbons for my parent chain must contain that functional group. All right, so I have to have these 6 carbons here as my parent chain, because I got to make sure to include that thiol functional group on my parent chain. So that means these 3 carbons over here would be a substituent, specifically an alkyl substituent. So this would be a propyl group. And I'm going to number my parent chain. Remember, we prioritize that functional group, making sure it gets the lowest possible number. So this would be 3 propyl, and then 2. My parent chain is a hexane thiol. All right, and remember we also could have another perfectly acceptable IUPAC name would be to move the locant of that functional group into the back half of the name directly in front of that functional group. So I'm going to take this same name but just reorganize it here. I could also call this 3-propyl hexane 2-thiol. Either one of these would be perfectly acceptable. All right, and we said that we had to use this format here where we put it in the back half of the name if we had both a carbon-carbon double bond and an alcohol group in the same molecule. We'll see the same sort of thing here. So let's do another example. All right, but before we can really do this molecule here, we're going to have to update that priority list that we created. So remember when we were talking about alcohol nomenclature, we had this functional group priority list. Where we ranked all of our functional groups, or at least all the ones that we had covered in the course, from highest priority to lowest priority. And those lowest priority groups were our 2 first semester functional groups, our alkynes and our alkenes. All right, we said that alcohols were higher priority than those 2. And now we're going to put in our thiols on this list. Thiols are above the alkenes and alkynes, but lower priority than alcohols. All right, I'm going to leave some room up here for these 2 things. First of all, what we've talked about before is referring to these functional groups by their suffix. So for alcohols, that was that OL ending. For thiols, that was thiol. For alkenes, that was ene, E-N-E or E-N. And alkynes were Y-N-E or Y-N. And I'm going to leave some room up here to complicate things. All right, but given what we've discussed thus far about alcohols and alkenes, and given now that we've introduced thiols onto this priority list as being higher than alkenes, I want everybody to take a second and name this molecule for me. All right, so first of all, I'm going to find my parent chain here, my longest continuous set of carbons. All right, we had these other steps here, so just to be good, the next step was to find and name our substituents. We don't have any for this one, but that next step was to number our parent chain. All right, so let's put in our two numbering schemes here. Okay, and which one of these numbering schemes is correct here, red or blue? Red. And why red? Because that thiol group has priority, exactly. When we number our parent chain, we're going to prioritize that highest priority group. All right, so absolutely. I'm not even going to pay attention to where the double bond is. I'm going to pay attention to where that higher priority thiol group is. That means I want to pick the red numbering scheme. All right, so this isn't going to be a hexane thiol, but rather a hexene thiol, right? Because I have that carbon-carbon double bond. But I got to specify both the location of that double bond and that thiol group. So I'm going to have to build these into the back half of the name. So this would be hex, forene. And we do keep the E on the end, even though we're not going to ram them together, directly together, 3-thiol. So hexforene 3-thiol is going to be the name of this molecule. And you would confidently enter this in on SmartWorks and it would be like, bam, wrong. What's missing? Stereochemistry of that double bond. So this is specifically the E stereochemistry of hexforene 3-thiol. Cool, but I said I left a little room to complicate things here. All right, we talked about these suffixes here for our functional groups, but many functional groups also can be referred to by a prefix, all right? Except for alkenes and alkynes, these only have a suffix version. All other functional groups, you also have a prefix for. So for alcohols, we would use the prefix hydroxyl. And for thiols, we would use the prefix mercapto. All right, so what the heck are these, and when do we use them? All right, so let's take another example here, another mixed functional group example. All right, and I want everybody to complete those first 3 steps for me, finding and naming our parent chain, finding our substituents. We don't have, well, we'll get to that. I guess really what I want you to do is put in the numbering scheme here for this chain, all right? And then we'll talk about how we're supposed to name it. All right, so my parent chain are these 7 carbons here. Am I going to number in this direction or am I going to number in this direction? Which one of these numbering schemes is correct, red or blue? Blue, because the alcohol is the higher priority of the two functional groups, so that's the one that I'm going to pay attention to when I number here. All right, so then what's this suffix-prefix business? Okay, so my higher priority group, I'm going to refer to by its suffix. The lower priority group, in the world of nomenclature, is no longer considered a functional group referred to by the suffix. It's going to be considered a substituent we refer to with its prefix. All right, so that lower priority group it becomes a substituent and I'm going to refer to that substituent by that prefix name. So in this molecule here, I'm not going to use thiol at all. Because this SH is the lower priority group, it is now a mercapto substituent. Meaning it goes in the front half of the name, so this would be 6-mercapto to heptanol. All right, so let's do another example here. All right, so I'm going to do my longest continuous set of carbons. That means that this 2-carbon chain right here is an alkyl substituent, an ethyl group. I'm going to number my parent chain, and I'm going to do so in such a way that prioritizes that higher priority group. And since this is my lower priority group, it's no longer considered a functional group in the nomenclature world. It's a substituent, specifically a mercapto substituent. All right, when I put my name together, which one of my substituents am I going to put first, ethyl or mercapto? Ethyl, because I'm going to go for alphabetical order. There's no longer anything special about that SH group in the world of nomenclature. It doesn't go first or anything like that. It's just another substituent, like all of our other substituents. So I'm going to put my ethyl in my name first because of alphabetical order. So 3-ethyl, 7-mercapto. Then we got that 8-carbon parent chain, my 2-octanol. Okay, so let's do one more example to kind of hammer this home here. Let's do a ringed structure. All right, everybody take a second and name this one for me. All right, so this one is kind of a deceivingly tricky one here. So first of all, what is these groups, the hydroxyl, the chloro, or the thiol group, which one of these is my highest priority group? That OH group. So that's going to become my functional group in my molecule here. My parent chain would be cyclohexanol. All right. Where is carbon 1 in this molecule going to be? That OH group carbon. And that's always going to be carbon 1, right? Because that's my functional group in my molecule. So I don't put that 1 in my name. Just by saying cyclohexanol, I know that that hydroxyl group is on carbon 1. So it's not 1-cyclohexanol, it's just cyclohexanol, all right? Next, let's look at our numbering here. So I can number in 2 directions. Again, starting at that functional group, I can go clockwise. Or I can go counterclockwise. And which one of these 2 numbering schemes is correct here, red or blue? All right, so I have a feeling a lot of people are tempted to say blue because they're trying to put this SH on the lower number here, all right? But this is no longer anything special. It's no longer the functional group in my molecule. So instead, if I look at these 2 numbering schemes, I have a 1, a 3, a 5, and a 1, a 3, a 5. I have a tie in my numbering. And how do we break our ties? Alphabetical order. So this here is a chloro group. This here is no longer special. It is just a mercapto functional, not functional group, substituent. And so when I go to alphabetical order, my chloro group is going to come first. So yes, I'm going to pick this red numbering scheme here to break that tie. All right, so putting this in my name here, this would be 3-chloro, 5-mercapto, cyclohexanol. All right, if we have these two functional groups in our molecule, we're going to consult our priority list. The higher priority in the world of nomenclature is considered the functional group. The other one is now demoted to that status of just being a substituent on that molecule. Cool. All right. Let's move on. We're going to talk about reactions of thiols and sulfides. I'm just going to note I'm not going to teach you all sulfide nomenclature. You can use your simple common names for ethers. I don't even know the IUPAC names for sulfides. You really don't see them too often in the wild. All right. But yeah, so we're going to focus on thiol nomenclature, but we are going to talk about some reactions here. All right, and both of these functional groups contain that same element, sulfur. And we've talked a little bit about this before when we made our list of nucleophiles. But these sulfurs, even when they're neutral, are good nucleophiles. Right? They have this lone pair that they can donate. Being a larger atom, they're an even stronger nucleophile than oxygens are. Larger atoms, their electron shells are like a little bit more squishy, right? So they can kind of get those electrons into an electrophile a little bit easier. And what kind of makes this even more true is that not only are there good nucleophiles, but they're also bad bases, which means that they're almost exclusively playing the role of being in substitution reactions. So if we take an electrophile, like an alkyl halide, and we treat it with a sulfur nucleophile, like hydrogen sulfide, also affectionately referred to as swamp gas, gives you a sense of how that smells, we're going to get a substitution reaction to create a thiol. All right, but importantly, this reaction does not stop here. All right, why not? Well, what do we say about these sulfurs here? They're good nucleophiles. So what's going to happen when we create this thiol here? It's just going to react with yet another molecule of our electrophile. So we would not get a thiol product in this reaction mixture. We would instead have them reacting with more of those alkyl halides, creating a sulfide product. All right, so this reaction will indeed create a thiol, but it doesn't stop here because that thiol is also a good nucleophile and will react with that alkyl halide. All right, remember something a little deceiving about our pencil and paper organic chemistry. It looks like there's only one molecule of my bromoethane here. But of course, when I'm performing this reaction, I don't have a single molecule. I have a beaker that has like a mole, 10 to the 23 molecules in there, or something like that, right? So there's plenty of this stuff floating around such that as soon as one of those thiols are created, it's going to turn around and react with a second molecule of your alkyl halide, creating this sulfide product here. All right, so then what if I really want to stop here? What if I really want to create a thiol? How do we do it? We can do it. It's going to require a little bit more, a little bit of a special reagent here, what's called thiourea. All right, so just real quick, this molecule here is what's called urea. A very important molecule in metabolism, you might have talked about it in a biochemistry course. When your body breaks down amino acids, proteins for energy, it has to package that nitrogen somewhere safe to get rid of, and it packages it into this molecule urea. Okay? Urea also plays a really interesting history in organic chemistry. All right, so just to take a step back, little fun fact history lesson. All the way, way long ago before chemistry existed, how did they explain the world around them? It was a very religious-based explanation, right? The church was really in charge of quite a bit, so why is the sky blue? Because God says so. That was kind of how the world was explained, all right? Then we had that scientific revolution that came along, and they were like, maybe we should test out these theories, get some evidence, and that's how we should come up with how the world works, right? So we had our scientific revolution that birthed all these branches of chemistry, physics, or rather chemistry, branches of science, chemistry, biology, physics, kind of all sprang up around that time. But that influence of the church was still permeated all of those science branches for quite a while, to the point where early chemists believed that, yes, we could explain the world around us using chemistry, using science, but we are divine. There is something special about us that cannot be explained by science, right? And it wasn't until somebody came along and isolated urea from the human body, really from urine is how we get rid of it, isolated urea, and then made that exact same compound from inorganic stuff that they get from rocks and all that other stuff, made the same molecule and said, look, this same thing that was in our body, I can make from scratch from other things. That kind of helped break down that barrier that okay, I guess we're not that special, and we can be explained by science. All right? So kind of the birth of organic chemistry as a discipline is kind of credited. Urea was kind of the one that helped tip down that wall. And anyway, we're not talking about urea in this case. We're going to talk about thiourea, which is when I take that oxygen and I replace it with a sulfur. All right, so this is thiourea. And thiourea, it can be used to create thiols. All right, so if I took my alkyl halide, my same alkyl halide, but instead of treating it with that hydrogen sulfide, that swamp gas, I treated it with thiourea. All right, I am going to have to do a second step here of treating this with dilute sodium hydroxide. But this will give me not a sulfide, but will stop at that thiol step, giving me my thiol product. All right, so these are our two we're only going to cover these two reactions here. So let's summarize. Let's take that alkyl halide and in one beaker, we're going to treat it with that swamp gas. And in our other beaker, we're going to use our thiourea. Everybody take a second and give me what my two products would be of this reaction. Of these reactions, rather. Oops. right, so remember, hydrogen sulfide, being that good nucleophile, will react with an alkyl halide, and we will get a thiol, but then that thiol is going to turn around and react with yet another molecule of that alkyl halide, giving me this symmetric sulfide product. All right, so one method is used to create sulfides. The other method would create a thiol. All right, so these are two reactions of our sulfur-containing functional groups. All right, so let's put them next to each other so we can really see the difference here. We take our alkyl halide and treat it with that very simple hydrogen sulfide. We'll get a thiol that will then react with another molecule of our alkyl halide to create our sulfide. Or if we use our fancy thiourea method, then we can stop at that thiol step. All right, and in both of these cases, we started with this good electrophile, this alkyl halide. Let's take a second and start to do some review from our previous chapter. What if I had this alcohol and I wanted to make a thiol? Everybody propose a synthesis method to convert an alcohol to a thiol. All right, so I'm trying to replace that hydroxyl group or substitute that hydroxyl group for that thiol group, for my SH. But remember, we had a problem with alcohols in that it's kind of hard to get rid of that hydroxyl group. It's a very bad leaving group. So we have to have this first step where we could have done a number of things, but we got to convert it into a good leaving group. So we could just very simply convert it into an alkyl halide. Right, using that thionyl chloride. You could have also turned it into an alkyl bromide using phosphorus tribromide. There was even a third method of converting alcohols into good leaving groups. Does anybody remember what that is? Yeah, that thionyl chloride. TSCl, that big ugly molecule there. All right, and then from there, now I have my good leaving group, so then I can go ahead and follow that up with that thiourea and our dilute sodium hydroxide. I guess that would be steps 2 and 3 in order to get my thiol. All right, so we've sort of covered all the new material for this particular unit. So it's a great point to go back and start reviewing. That discussion of alcohols was like 2 weeks long, right? It was quite a long chapter and we learned quite a bit. So now is a great time to sort of rewind back and start reviewing for that exam next week. Again, we got our functional groups that we covered in this unit. Alcohols, ethers, epoxides, and now we know about thiols and sulfides.